Good morning, everybody. My name is Stefan Bretzke. Like Fiona Williams, I'm from Ericsson as well, and I will go a little deeper into some of the aspects of 5G networks again. So some of the slides you have already seen now. And the topic is ICT for smart grids with up to 100% renewables. Up to means that we are on the way to replacing all the conventional energy sources, as you may know. All right, so very welcome. What you see here is actually some 5G equipment already with an antenna. The actual base station is in here. The antenna is not part of the base station. The actual base station is here in the box, okay? And it's fenced in so that other people cannot play with it too much. Yeah, this is me. I'm not an electrical engineer. I'm a computer scientist working for Ericsson since 1991 as a project manager in 5G technology. And I'm more of a teacher type personality, so please interrupt at any time. I will talk much slower as well, okay? So that you have more chance to take notes and follow and interrupt me also. So please interrupt whenever you feel like it. Okay, these are the 4 modules in my session. Development of mobile telephony, 5G technology and benefits, and then the application in voltage control and frequency control. I hope you got general introductions yesterday already from voltage and frequency control mechanisms. Marina, right? They did. Okay. All right, then we start with module number 1. That is the development of mobile technology. Ericsson itself started in 1876, so that's quite old, as a telegraph workshop. And today it's a leading provider of ICT or communication services, not only to mobile network operators, but also to other companies who may wish to use communication equipment. And the idea is that we provide end-to-end solutions. This is quite different from other providers. Many other providers produce some or develop some pieces of the mobile network, but Ericsson is really the only one that does everything, including billing and charging and lawful interception, etc. Nobody else does that, not even Huawei, and that's one of our marketing benefits here. And so we have lots of extra solutions here included, operational support systems, business support systems that includes billing and charging, and other stuff. We don't work with fixed networks anymore. That is old technology, legacy technology. We still have to support it, but we don't develop it anymore. We provide IP transport networks. That means switches, routers, and similar things. Microwave systems, firewalls, etc. And we clearly don't develop mobile phones anymore. That stopped in 2011 already. So because that market is really difficult, and as you can see today, only Samsung and Huawei are making money out of it, and Apple, of course. But all the other companies are losing money, so it was good that we left that market. It's too volatile. Okay, we start with a little exercise. Suppose, very simple use case, Anna wants to call Robert. What are the necessary steps for the mobile network so that Anna can actually call Robert? So what do you think is necessary for this to work? Any ideas? What does the mobile network have to do? No clue? Yes, please.
It is sure that Anna's phone somehow needs to tell the base station that she's in the range of this base station.
Yes.
She wants to make a call.
So the phone of Anna has to be connected to the mobile network, let's say, right? Otherwise, she cannot reach the phone. Okay, that is the first part, right? And then Anna has to be authorized also to make phone calls. Maybe her prepaid card is finished, then she's not. Okay, So all this has to be checked before the call is even set up. Okay, what else? The same for Robert. Robert has to be connected to the mobile network at the moment and not be in a tunnel or in one of the famous Funklöcher in Germany. Otherwise, you can't reach him or her. Okay, fair enough. And even Robert has to have some money left on the prepaid card because otherwise you can't make the phone call. What else? Well, first of all, maybe Anna has a subscription from Italy, but is currently in Germany, right? And then, first of all, the German company has to check with the Italian company if Anna is still a registered customer, or if she, in the meantime, got kicked out from the network because she didn't pay the bills. That's the second step. Then the next step is, okay, Anna is in Germany, but the Italian company is involved as well, and maybe Robert is from Britain, but is currently in Luxembourg. So then the mobile company in Germany will first try to find Robert by contacting the British company, because Robert has a British subscription, right? And then the British company will hopefully tell the German company that Robert is currently in Luxembourg and that the call has to be forwarded not to Britain, please, but to Luxembourg instead. And all this has to take place in a fraction of a second. Okay? So first of all the people have to be registered, right? People have to have money on their prepaid cards, etc. So they have to be in good standing. They have to be authorized to make phone calls. And and you have to know where people are. Finding people is called paging in English. Okay? They can be anywhere. And there are databases for that. So Robert's phone company has a database registering where people are, in which country at least they are currently. Not exactly where they are. That then is the job of the Luxembourg company to know exactly where Robert is currently located in Luxembourg so that the phone call can be forwarded to the right city or region or a base station in Luxembourg. All right? That's only a small part of it, but I think you get the idea that this is quite complicated, so it's not so simple to set up a call. And that's why it's always also failing in a number of cases, because anything can happen, like Robert's subscription went out, or et cetera, or he's currently in a tunnel or whatever. Okay, so this is, first of all, the first question then is Anna really connected? I mean, not Anna herself, but hopefully Anna's phone is connected to a base station. Anna will then request to set up a voice call. Is she permitted to do so? Where's Robert? Maybe he's at the area, even on the same base station. He could be just outside the door here, or same area, same network, or even the same country. Are Robert and Anna customer of the same network or not? Is the phone active and turned on? Or what is called forwarding? Do you know that? Maybe Robert doesn't want to be disturbed because he's suddenly currently sitting in a PhD summer course here at the university, so all the calls go to a different phone from the secretary or a fixed phone at home or whatever. That's called call forwarding. Right, and then also the speech quality has to be agreed. Depending on your subscription, different speech qualities are available, and only if both Anna and Robert have the same high speech quality, then you get a better speech quality for the end-to-end connection. Or charges apply. In America, anybody using the mobile service has to pay for the call. So even if you receive the call, but not on a fixed phone, but on a mobile phone or cellular phone, you have to pay parts of it, okay? Plus tax. And the tax in US is very volatile. So determining the charges for a phone call is not trivial at all, okay? But that's, of course, not the topic here. Charging and billing is a separate topic for business people. And then mobility, what happens if Anna moves? Maybe right here, we are very close to the Dutch border. What happens if she moves over to the border into the Netherlands, or goes to the three-point corner there and suddenly is in the range or even of the Belgian operators, right? It's quite chaotic, and sometimes then the calls get interrupted because international roaming doesn't always work perfectly. More questions on that? So Anna and Robert can move, of course, and if they move too fast with LTE, then the calls get disconnected too. But with 5G, they test, I think, up to 400 kilometers per hour that the call, even if they sit on the Shinkansen in Japan, do not get disconnected. All right, these are the basic network elements in a mobile network. So we have our user equipment. That must not be, or that doesn't have to be a mobile phone. That can be quite anything. Fiona mentioned a few devices already, IoT, Internet of Things, modems, etc., smart meters for getting your gas bill, etc., etc. All sorts of terminals, and all these terminals would probably have a subscription. Traditionally, the subscription means that you have what in your phone? A SIM card. Yeah, that is, of course, very difficult to manage if you have millions of little devices. So for these devices, there are software-based SIM cards, so that the operator doesn't have to hand out SIM cards to each and every smart meter, right? I think in the phones, you will still see the SIM cards because it's kind of convenient. Even if you want to keep the subscription but change the phone, you just move the SIM card from one phone to the next, which is kind of nice. But for smart meters or other hardware devices that are not personal, that's not necessary. And we talked about the base station here. This is where the key changes in 5G will come, right? The interface here, the air interface, that is where the drastic changes are with the massive gains in latency, transmission speed, and in throughput. What is this? Hello? I didn't touch it. Can you please? I didn't even touch the computer. Can I press something? This is still the right slide.
No.
Sorry for this interruption, especially for the people on video.
Okay.
Verschwommen angezeigte Apps. Aha. Don't want to touch it, really. But I need... All right. Yes? Now, but only since 20 seconds. I can what? Abbrechen. I hardly dare touch it anymore. Okay, I think we covered this. So this is also where the video can be cut. Yeah, network elements we touched already. Base station, I said that the key changes in 5G initially are here on the air interface, which is where the primary gains are achieved when it comes to speed, data bandwidth or throughput, and all the other aspects, okay? Backhaul means just a connection, as Fiona said. Usually it's a wireline connection with fiber optics, okay, to reach really high bandwidth, but it's also possible to set up microwave directional connections between two places. Then here we have a radio network controller, somehow controlling the base stations, and then the core network. The core network has all the intelligence. The core network is the thing in the mobile network that knows where people are, for example, or can find that out. The base station is not involved with that at all, right? And of course, we're not only talking about people anymore, this can be devices as well. And the device can move as well. Even a train can have a device built in, and that's not a person, obviously. So whenever I say subscriber or something, it can be a device just as well as a person. Okay, all the intelligence, data handling, data processing, charging, location, etc., even lawful interception. Do you know what that is? Lawful interception. No, it means, oh, please. Okay, yeah, I'm not allowed to touch the table here. That's the problem. This is very shaky. So just unplugging it in, maybe. Yeah. So the table is. Don't touch the table. Right. Do you know what lawful interception was? That was my previous question. It means that legal authorities, such as police, Secret Service, NSA, Russian Secret Service, etc., can listen in and copy your data or your phone calls. Okay? And in Germany, if a judge orders that, it is a legal procedure. That's why it's called lawful interception. There's also unlawful interception, but that is not provided by Ericsson. Right, and then we have gateways, and through the gateways, you can connect to the rest of the public internet. Okay, this is the basic. Jesus. Yeah, the basic technology. These are the standards. Fiona mentioned them already. So it started all in the late 80s with GSM, which is also called as second generation mobile telephony. And then there were enhancements, and for the first time, digital packet transmission, so IP-based packets could be transported, but that came like 5 years later after GSM was introduced. And then the capacity was enhanced with Edge. I'm not going into any details. 10 years after GSM, you had UMTS, 10 years later LTE, and 10 years later 5G. So it's very easy. It's always a 10 years gap between these standards. And all these things here on the right are improvements for the bandwidth of the packet transmission, of not for voice traffic, but for IP packet transport. Okay, so these are the logos. All this is standardized nowadays through one standardization body, which is called the 3GPP, the Third Generation Partnership Program. Even if it's not about third generation anymore, it doesn't matter. They still standardize 4G and 5G too. And in 5G and standardization, you have hundreds of partners, companies like Huawei and Ericsson, but also all the key mobile operators like Vodafone. And the biggest one in the world is China Mobile, with more than 800 million customers. And many others, right, are in there, and they control the development of the system. Okay, I'm not going through the changes, just a few aspects. So first, after voice calls were possible, then you had the short message service, and very, very limited internet access initially. Then the throughput or bandwidth increased all the time. The voice quality got better. The latency, do you all understand what latency means? Yeah, it's the number of time or the amount of time it takes to transmit packets from A to B, basically. Okay? And in the mobile network, it's always from one terminal into the core network. Full stop, not end to end. Then faster setup time. Setup is like a call setup that I explained when Robert calls Anna, that the process just until you hear the ringing tone is shortened. Okay? When you dial a number or set up an IP session, how long does it take until you hear the first ringing tone, until the actual session might start? Then it's a full IP-based network now, not in 3G, 2G. And we have Internet of Things for communication between machines. And here in this table, you see the bandwidth or the throughput per session for packet transmission. So in the beginning, you had 0.09 megabits per second. That wasn't much, so it was not much fun to watch any Amazon Prime videos on that. And then came Edge 5 years later, and then it increased a little bit by 30–40%, not much. Then UMTS, 0.16 megabits or 160 kilobits. And then HSDPA, or high-speed data packet access. That was really the first major improvement when you had suddenly 12 megabits per second, then 100 in 4G and 10,000 in 5G. All these numbers are great, but they are more or less per cell. So if the cell is very busy, like you go to a trade fair or something, or you sit here in the lecture with 1,000 other people, then obviously you don't get 100 megabits per second for yourself, right? Because that is limited to, depends on the number of people or in the area of one base station. Questions? No. Okay, then we look at the benefits of the 5G technology as far as they are relevant to us. So I already mentioned that the standardization is done by 3GPP, which is a huge partnership program where lots of people are there, lots of different interests also. So it's really hard to reach an agreement if you have 200 people discussing it. As you may imagine, some people have more to say than others, but still it's difficult to reach agreements. And Fiona already mentioned these 3 business types or business cases for 5G. Enhanced mobile broadband, that is the traditional mobile telephony, video watching, etc. Then we have ultra reliable and low latency communications, for example, for autonomous driving or electronic health. This may be very relevant. And then massive machine type communications. That's if the number of devices is really enormous, it's really huge. Typical example for that would be smart metering, if everybody really has such a device at home. And the global launch is this year, and until we see that in Germany, I think you can easily add a year or 2, because the auction for the frequencies is not complete, and Vodafone and Deutsche Telekom have taken the government to court, so it's not likely that the auction will happen anytime soon. Okay, another important part of 5G is then Internet of Things. There are different standards. A key one is Cat-M1, which then supports massive number of devices with very short latency times. The important thing is that devices are cheap and that the devices use very little energy themselves. Hopefully they can be connected to a battery even. So, and you don't want to replace the battery. So it would be best if, say, a smart meter only transmits data once a day and not continuously, because that will drain the battery, right? So the idea is that you have very cheap devices which only transmit data very, very infrequently. And then they live long, and the plan is that the devices can be used for 10 years without changing anything, okay? Then the transmission must be very robust. It's not so important that you have large amounts of data. That is not the case in Internet of Things. The focus is more on that you don't lose any data, right? Because smart metering, if you take that example, the operator, the DSO, distribution operator, or the service provider must not lose any charging relevant data. Otherwise, the invoice is not correct, and if the invoice isn't correct, then the customer can take the company to court. Then optimize for frequent and high performance devices. That is also possible in some cases. You will have very devices, for example, in a train, monitoring devices that film the tracks. Then you have high data volumes as well, and lots of data also in a short time frame. So all this is included. Overall, these are the key features of 5G. So let's take it from here. Mobility. That's a key improvement in 5G. Mobility means that the devices can now travel up to 400 kilometers, and the connection is not interrupted. We will see if that is working on the ICE train system, but okay. Then the next one is spectrum efficiency. Spectrum is the radio frequencies, right? How much data, how much bandwidth can you actually transmit or transport over any given bandwidth or over any given number of megahertz, etc. in the spectrum. Then user experience, data rate, that I think I don't have to explain. What is the data rate or the bandwidth that the actual user sees? Then peak data rate, what is the maximum achievable data rate? Then the area traffic capacity, how much traffic can I really have in one cell? Network energy efficiency, how much energy do I need to run all these base stations? The core network is irrelevant when it comes to energy consumption, but the base stations, because they transmit all the time, they waste approximately 1,000 to 1,500 watts continuously. So this is a key aspect also, that we look into that and that we try to reduce the energy consumption of the mobile network. And what would you do about that? There are at least two ideas. One is beamforming, that the antennas direct their signal to areas where lots of people are and don't transmit so strongly, if at all, to areas where there's nobody in the forest or something, right? That's one aspect. And the other aspect is that you modify the signal strength over the time of day. So at 3 o'clock in the morning, unless it's New Year's Eve, there's probably hardly anybody using the system. So you can definitely wind down the signal strength and even switch off many base stations, okay? So there are lots of ideas here how the energy consumption of the actual mobile network can be reduced. In Germany alone, you can say that we have round about 200,000 base stations. So it's quite a considerable number. And then finally, connection density. How many devices can there be per square kilometer or whatever, right? And that is drastically improved. And we have three different use cases or business cases, as I explained. Enhanced mobile broadband, that's the traditional phone user and video watcher spectrum here, where people want a very high data rate and they want a very fast transmission. And then we have the two other use cases. One is the massive machine type communications, where you have the most important parameter here is the connection density. And finally, the ultra reliable low latency communications, which is what is relevant maybe for distribution system operator in the electrical grid. They want low latency and possibly mobility as well. All right. And now these are all the benefits. Let's summarize them. We have low latency. I explained that. For some cases like frequency control, as I will explain in a minute, it's important that we have very low latency so that the system can react very quickly. We have different types of quality of service classes, which is related to the next one, network slicing. Quality of service classes means that some types of traffic have priority over other types of traffic, right? So sending WhatsApp messages will probably have the lowest priority or quality of service class, while critical infrastructure messages or alarms or whatever will probably have the highest quality of service class. Network slicing means, as Fiona already explained, that you separate all the elements, buffers, waiting queues, etc., and that traffic from YouTube users does not interfere with traffic from DSO infrastructure providers. Then coverage indoor. So 5G will change very much that the coverage indoor, inside buildings, even in the basement, is getting better. Coverage in rural areas is getting better too. How? By transmitting on very low frequency bands, like 700 megahertz, which was before used by television systems and stuff. So using frequency bands which have very limited bandwidth, probably. 700 megahertz is not good for transmitting large quantities of data, but at least you can reach everybody for tons of kilometers in a radius around the base station. Okay, machine-to-machine communication, we've mentioned, low-cost, low-energy devices, high-volume data available if needed, and finally, two more things. Global security mechanisms. The system is used globally, and the security standards are very sharp and very constantly improved as well, and then it's a global standard, so any device that you produce for the German market will hopefully also work in American market. That's not exactly true because the frequency bands are not standardized. So an Apple phone from America will not work in all frequency bands in Germany and vice versa. But in principle, it is like that. Okay, so these are the key aspects for reserve. Very high availability. That's very important. The DSOs or the distribution system operators, they want to make sure that when they want to collect data, that they get the data. So it's not acceptable that the system is out for an hour or two, right? So availability, the network, the mobile network must work basically all the time. That's what this means. Then the latency for certain aspects, like frequency control, the transmission must be very fast. That's the first one. And finally, the network slicing, we don't want to be disturbed by people sending Happy New Year messages on the 31st of December. So that's why we want network slicing, so that the DSO traffic has clear priority over any other type of traffic. All right, questions? No, and I think I will skip that because we're a little late already. Yeah, just a word on maybe what this slide explains is actually latency. So the complete latency is the end-to-end transmission time from basically the inverter and the electrical grid, which is connected to some 5G device, 5G radio interface, some base station, some fiber optic cable, some mobile core network, another fiber optic link, and then hopefully here you have a frequency data manager or some kind of control system for the DSO, whatever you may have. All right, and that's what we define as latency in this project. And then the availability, what customers can expect is availability of 99.99%. That sounds pretty good, but it means 4 minutes and 23 seconds of mobile network downtime per month, which is not much because even the operator has to restart the systems sometimes or update the software. And if you only have a window of 4 minutes and 23 seconds every month, that's not much. What can you do about it? If you were a mobile operator, how would you solve that puzzle? Yeah, but even this 4 minutes includes the night times too. Because even at night, you hopefully want a smart grid that is working, and you want power even at night, right? Otherwise, all the freezers stop working and whatever, and all the electrical heatings in Norway and Sweden and other countries which use electrical heating would not work. No. Other ideas?
I would use cluster simultaneously.
Yeah.
And only have this one at a time.
Yeah.
So the capacity remains enough. And at night, we don't need so much capacity. So one of the clusters can be shut down and upgraded. Yeah.
Okay. I think you're going in the right direction. What the keyword that you're looking for is redundancy, so that you have connection to more than one base station at any point in time. So even if one base station is getting upgraded, that you still have connection to a second base station somewhere in the area. So everything basically has to be duplicated, and you want to be in the area of several base stations, core networks, etc. So even if one node is down, that you still have full availability of your data transmission. All right, so there's planned downtime, which means planned upgrades of the system, changes of the configuration, anything that the mobile operator has to do once in a while. And then there's unplanned downtime, which means software errors, hardware defects, other outages, etc. And as I said, maximum reliability requires duplication of hardware and software, and the term for that is redundancy. I guess you have that in electrical networks as well, although it's possibly more expensive there, depending on the hardware. Then network slicing, already explained. Network slicing really means that you have different use cases. Here, smart metering, cars, medical, smartphone users, logistics, IP television, etc., etc. And they all get their own virtual network. Okay? The network is only virtual. The physical stuff exists only once. But inside the physical network, you define several virtual networks which are completely separate from each other, so that the data is transmitted without any problems. Okay, and all these are different parts of the network. I'm not going to go into that. Just one reminder here is a part of the base station and the radio equipment. Everything in the mobile network that you have today, which is dedicated hardware, dedicated software, etc., all this will disappear in the next 10 years and will be replaced with virtual software. So in the future, Deutsche Telekom can just buy the hardware from Dell and then get the virtual machines and operating systems from Ericsson or even VMware or whoever, and then just load different software on top of that. All right, this is what I think was done in the basement here in this building. This is what a 5G prototype base station looks like. This is not what the commercial products will look like, of course. And this is what the 5G modem looked like. It's quite big. So as you can see, the development is not finished yet. Then the platform, Fiona explained that already. I will skip that. So we have the first two chapters already covered. Then we look. Marina, should I take a 10-second break or what for the video? No. Just continue. Okay, then voltage control. I hope yesterday Sriram and others told you about voltage control and what different solutions there are. I'm not going into any details now, but assume that we have a distribution network, low voltage network, then you have different prosumers. If I use any words that you're not familiar with, do interrupt. The households that produce energy as well are connected to the grid through inverters. They can have solar panels, or they can have wind turbines, or maybe they even have a hydro power plant in the backyard. I don't know. And then they have inverters, and they're connected to the grid. And this is what voltage systems look like. And traditionally, the voltage control was centralized and located in the secondary substation automation unit. And this is not suitable anymore because the number of devices will increase continuously, and many people now have solar panels on the roofs. So there are two algorithms proposed. One is dynamic voltage stability monitoring, and the other one is active voltage monitoring or active voltage management for steady state problems. I'm not going to explain those. Hopefully they were explained yesterday. Do you know? Yeah. They were explained? Good. Okay, so what will change is that we have now communication channels from the inverters basically to some logic, some computer here, possibly co-located with the secondary substation automation unit, and their algorithms monitor from various points the voltage all the time, and then either activate or deactivate some of the inverters to make sure that the right amount of energy is fed into the local grid so that the voltage is stable. That's very, very high level, but I think for the detailed aspects of voltage control, you better talk to Sriram in the back. This is the communication network, very simple, okay, DER. It's not the Deutsche Reisebüro, but distributed energy resource. And they are all connected through 5G networks then with the secondary substation automation unit. Advantage is also that you don't have to put power line cables anymore to each and every household which is producing energy, especially with farms, etc. That could be quite difficult. And the same goes for the medium voltage network. Yep. And I think that's it. And then the second part is frequency control. Frequency and voltage control are not the same from the communications point of view. The latency requirements in frequency control are much more strict. So you have to be able to detect if the frequency starts changing, even by a fraction, and then you counteract or respond immediately. In voltage control, you have a few seconds and nothing will happen. In frequency control, it's really helpful if you can respond and act in fractions of seconds. That's why 5G is particularly useful. Okay, and frequency control, I hope that was explained yesterday as well, is grouped into different time zones or time areas. The first one is called the inertial response, or then we have primary control here, different response times, secondary control, and then the later times are tertiary or generator rescheduling. I'm not going into all the details, but for the communication part, inertial response and primary response are the key ones because they are time critical. All the rest, yeah, can happen whenever. And this is what the entire network looks like. And this is what the communication network will look like. So it's quite similar, you may think, but there's a difference. The difference is that in the voltage control, you had here your controller, and that took the decisions and basically instructed the prosumers or the households what to do. Here, not so much. In frequency control, it's much more likely that we have distributed and decentralized algorithms so that the DER itself can actually monitor what's going on and with the frequency in the grid and take action itself. It will still communicate the data to some frequency data management so that it can be monitored on a central level, but each device here is more likely to get data maybe from its direct neighbors and check if really if there's a minimum deviation in the frequency on the local grid here, and then take action. Okay? So two different aspects between voltage control and frequency control. Frequency control needs lower latencies, faster reaction, and is more decentralized, more distributed than voltage control, even on the local level. And that's all I have for today. Thank you for your attention. And if you have any questions, I'd be happy to hear them.